morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 7, that is Artificial Intelligence Enabled Control in Distribution Network. We have completed the AI control for the DERs for the distribution network, and now we came to the last level of your power system, that is your customers. So, how you can use AI for the consumers. So, the application of AI in the consumers are very vast. You can do the load forecasting, you can do the energy forecasting, that is the forecasting application. You can do appliance classification for the demand side management application. Okay? Like critical and flexible appliances present, you identify them for non-intrusive load monitoring. Okay? Then you can also use demand response strategies, that means schedule your appliances for the benefit of the customers. That means your energy management purposes, that you also can do with the help of AI. So, first application we will see, that is the data driven load forecasting. So, classification by duration of the method. How many types of load forecasting you have? Demand forecasting is categorized based on the forecasting duration and the methodology. Okay. So, depending upon that, how much duration or how much methods, which method you are applying, it is qualitative and quantitative methods you can use. When you have less amount of data, you do not have much data, then we go for qualitative method or qualitative load forecasting. What we do? Let us say you have multiple points here, we do a curve fitting, that means we see what is the trend of the load curve, that is a curve fitting plot. But if you have a huge number of data set, huge size of data set, then we go for quantitative load forecasting, and that is done by regression, ANN and fuzzy logic and other kind of deep learning technologies. Okay. So, depending upon that, your forecasting techniques can be broadly classified with traditional, modified traditional soft computing techniques. And now, depending upon what is the time frame of your load forecasting, there are 4 different kinds of forecasting techniques. One is called very short term load forecasting, where you are predicting the load for minutes in advance of the real time grid operation. That means you are doing it for 1 minute ahead. Then you have short term load forecasting, where you are doing it for 30 minutes to 15 days ahead. Okay. Then you have medium term, which is for monthly and the yearly basis. That means the forecasting you are doing for 1 month prior or 1 year prior, that is called your medium term load forecasting. Then at the last you have long term load forecasting, which is for the years to decades, that is normally used for the planning purposes, that you want to see how much load growth you are going to experience for the next 10 years or 20 years down the line. So, at that time we use this long term load forecasting. Other this work generally used for the operation of the system. Medium term load forecasting, sometimes we do for short term planning, this is for the long term planning, and short term load forecasting and the very short term load forecasting we use for operation of the customers or the distribution network. Okay. So, which kind of data you required for your load forecasting? Obviously, first data that is required for each and every AI tool you used in the distribution network, that is the weather data. But whatever you do, your management of the network, your generation of the DERs, even the load pattern, that depends upon the climate or weather for that particular day or time or month, that is required. So, always you require the temperature, wind, humidity and cloudiness data for the from the meteorological department. Second, calendar, for which day it is a holiday or it is a working day or it is a weekend or weekdays, which day you are trying to predict for your load. So, that data you need from your calendar. So, that is called calendar data. You need rooftop solar power generation, because now we have solar power generation in the load. So, if you have solar and then you have load, if it is a solar and if you have your load, if you see in the meter, what you will see? It is a net load. So, your actual load is masked behind your solar power. Okay, you are just seeing the net load, but that is not your actual demand, right? If some days this solar goes out of order, at that time you will ask for your total demand. So, first you have to know how much solar power generation is there and how much masking is happening with your total demand. So, your rooftop solar power generation is needed to track due to their to track your load, because it is unpredictable power generation you have at your rooftop. Then economic condition of your customer, it is a commercial customer or industrial customer or residential customer, how they are using their energy, is they are very critical, they are very flexible, or they are in between critical and the flexible, or for certain time they are flexible and certain time they are very strict. So, this kind of economic condition and the energy usage pattern, you have to gather that knowledge. Then consumer behavior, the type and number of the appliances, especially AC system influence household electricity consumption, their data you also need. That is the behavior of the consumers. Okay. Then obviously the new type of load, that is your electric vehicle. So, how many electric vehicles you have in your network, or it is going to be added at the evening when they will come back from the work, that data also you need. So, the forecasting technique, generally we followed the traditional technique is a regression method, multiple regression method, exponential smoothing, iterative reweighted least square method. This is little bit changed in the modified traditional, where you use adaptive demand forecasting, stochastic time series forecasting, autoregressive model, autoregressive moving average model, and henceforth. For artificial AI techniques, we use genetic algorithm, fuzzy logics, neural networks, that means artificial neural networks, and knowledge based expert systems. So, what is those traditional data driven load forecasting technique? First, we will see the regression method. It is a statistical technique used to model and analyze the relationship between the dependent variable and one or more independent variable. Your dependent variable is your load, your independent variable is whatever data you have collected, that is your weather data and other data you collected. So, your actual load depends upon your previous load or standard load. That means you have some idea that if it is a weekend or a festival, the load should be higher. So, you have a standard set for it, plus little bit of your weather influence. This is your AI is the coefficient which relates your weather with your load data. That coefficient you have to know, and that varying, that is a varying coefficient. So, that is your independent quantity plus some noise. Obviously, we add some noise to give some flexibility to the prediction process. Okay, there is a white noise component. Then the second method, that is called multiple regression method. What do we do? For multiple regression is the most popular method and often used to forecast the load affected by number of factors ranging from meteorological effects, per capita growth, and electrical prices. So, other than having only one controlling parameter for your load, if you have multiple controlling parameter, which is generally the case, we use the multiple regression analysis, and there we use this formula, where this AT is the coefficient matrix for different controlling parameters. Okay. This is your independent parameters and this is the error, Gaussian error you have added with the to get the load value. Then you have exponential smoothing. What it says, in this method first load is modeled based on the previous data. That means you did some prediction or you have experienced some load previously as well in the weekends or weekdays. So, take that data. Then to use this model to predict the future load. Okay. So, fitting function vector, you will get a fitting function vector from your previous. Let us say you will see that my load is always goes like e to the power minus x, it always follows this architecture, that means always decreasing, or you can say it is always x 1 minus e to the power a minus x or 1 minus e to the power x, any kind of curve fitting you can get, or it can be a x square plus b x plus c, a quadratic form. So, this forms you will get from your previous load data you have incurred. So, fit that function to here depending upon the time. Okay. And then you add the coefficient vector and add some error with it. So, you will get the actual load for your current time frame. Then iterative reweighted least square method, what it says, the method uses an operator that controls one variable at a time and determining the optimal starting point. Autocorrelation function and the partial autocorrelation function are used for the resulting differenced pass load is utilized to identify suboptimal model of the load dynamics. Okay? We are using autocorrelation function to get the dynamics changing with the previous load pattern. A three-way decision variable is formed by weighting function, the tuning constants and the weighting sum of the squared residuals in identifying an optimal model and the subsequent parameter estimates. So, this is the equation we follow for iterative reweighted least square, where y is an n cross 1 observation, that is your load, x is an n cross p matrix known as the coefficient, and beta is a p cross 1 unknown parameters. That means your load value. This is your known value, this is your coefficient and this is your unknown value. Okay? And E is your random errors that you can incur, different kinds of error you can add. Now, the modified method, these are all traditional methods we have seen. Now, what are the modified methods is followed for load forecasting? That is, the first is the adaptive demand forecasting. What it says? Demand forecasting model parameters are automatically correlated to keep track of the changing load condition. That means your model is always learning and keep track how your load pattern is changing over the time or with the rolling horizon that you are storing. Hence, demand forecasting is adaptive in nature. Then you need not to always train with from the scratch your model, because it is taking the data, it is predicting, it is seeing what is the load pattern and then taking that as an input to the learning module, and from there it is modifying its training process. So, as an online software package in the utilities control system. Next, state vector is estimated using current prediction error and the current weather data acquisition program. State vector is determined by total historical data analysis. Okay? Then you have stochastic time series model. Time series methods are widely used to short term load forecasting process, because this is mostly a time series prediction. 12 o'clock this is load, 12:05 this is load, 12:10 this is load. So, every times we are normally we do the load prediction as a time series prediction due to their ability to model internal data structure like trends, seasonality and autocorrelation. So, we will see how this time varying, like the seasonal time varying or the your trends in the load pattern is related with each other, is correlated with each other, that correlation is validated. This method focuses on identifying patterns in historical data to build model and can accurately predict future load values over time. So, you will see the pattern, you will see the correlation between different method, different input data, and then you feed it for the prediction tool. It is used for autoregressive model, autoregressive moving average model, etc. So, first we will see autoregressive model under this stochastic time series. What it says? Autoregressive model can be used to model the load profile if the load is assumed to be linear combination of the previous load. That means, you have seen that yesterday my load is like that and today the load can be like that. There is a correlation between them. Let us say we say that from 6 p.m. to let us say 10 p.m. my loads are high all the days, and from 10 p.m. to let us say 6 a.m. they are at the off peak, and after that the customer is going out, it is going for his work, and at that time your load is falling down to close to 0. So, this is the pattern always the load profile follows. So, that means your previous load is assumed to be a linear combination. So, there will be some variation in the load values, but the pattern will remain same. If that is the case, then you can use it autoregressive model and express your load value as a linear combination or a linear equation with some error introduced. Okay. The unknown coefficient in the equation can be tuned on online using the least square method. So, this coefficients you will tune like a state estimation method, we use least square method, here also you can use least square method to tune it properly. Then autoregressive moving average model, which is called ARMA model. ARMA model represents the current value of the time series yt linearly in terms of its values at previous period. That means, we will say that let us say we have started with 12 a.m. and we started our prediction now at here, let us say we are at the 6 a.m. So, ARMA model says that at 6, let us say 6:05 am, whatever load will get, that is a combination, linear combination of its previous loads time as well. So, that we are getting y t equals to y t minus 1, alpha to y t minus 2, alpha n y t minus p. So, previously how many prediction you have done, because it is a rolling horizon prediction. So, previously how many predictions you have done. So, your current prediction is a linear combination of an weighted linear combination of that previous predictions. So, you can write it like this, within adding with some white noise. Obviously, we always add the noise or the error to give some flexibility to the prediction process. So, now we will use the soft computing or the artificial intelligence process for the load forecasting, and that is your ANN. So, short term electrical forecasting using back propagation neural network. The data collected, that is the day time, day or night, and weather, temperature and humidity. So, data collection, load, ambient temperature and humidity and wind speed data of a December month of 2010 is used here. The training data is split into 7 groups, each group containing data from a particular weekdays. Okay, like 7 days, Monday to Sunday, you have different data and you just segregate them or sort them like this. Then 7 different neural networks are trained for each day. For Monday you have one neural network, for Tuesday you have another, for Wednesday you have another, with the 7 different training data sets. Okay. The trained neural network is tested using a data over a period of 1 week from 25th December to 31st December 2010. So, this is your input data, historical weather data, this is your temperature, precipitation, wind speed and humidity. This data, historical data you have collected. This is the load profile for the time step for the 1 month time, and now this is your temperature data for that 1 month time. Okay. Use that ANN module having 2 hidden layers, one output layer, you have calendar data, weather data and consumer data. You fit those data in the ANN module and note the mean absolute percentage error as your loss function. And you plot, after plotting the predicted value, you can see the actual and the predicted value are close to each other. So, with the ANN you can see that you have predicted properly. So, the soft computing module is also good for application of the ANN tool, similar to the traditional, where in the traditional model the problem is that it is not learning, it is just following the path. Okay? That means the linear combination of it, or you have to get the curve fitting function. So, it is not learning. If your curve fitting is not good, then your solution will be bad. But in case of soft computing with the ANN tool, it is learning from your day, from your data set, which day you are doing the prediction, what is the climate data. From there, it will decide whether it is a linear combination or a non-linear combination. Not the user or not the designer is deciding. Previously, with the traditional and the non-modified traditional method, we are deciding that it is a linear combination. But it is not true always. Always your climate data is not linearly dependent upon your load, or your load is not linearly dependent upon your climate data, or load is not linearly dependent upon the weekdays or weekend, the day and time of the time frame. It is not linear. Linear dependency is very rare in the actual system, but for those traditional methods we consider it to be a linear method. So, if that is there, then your prediction accuracy will be very low. But if we go with this soft computing ANN or fuzzy logic, so if we use that, then we are allowing our AI tool to decide the correlation or the relationship between the input data set and the output predicted data, load data. So, that is more beneficial and you can say more superlative or more advantageous for the actual load prediction of the system. Now, we will come to the next application, that is the appliance identification using a deep learning module, that is the convolutional neural network. Non-intrusive load monitoring is getting attention to identify loads without human intervention. Okay? Deployment of demand side management and demand response algorithm needs knowledge of the connected appliances, because if you want to do the demand side management, first you have to know that whether you are connected with a flexible load or a critical load. So, how will deal with that? How will come to know? First you have to identify or you have to classify which loads you are equipped with in your home. Okay? So, for that, a multi-scale sinusoidal kernel based convolutional neural network model, which is abbreviated MSK-CNN, is proposed using 15 primary and 225 multi-scale sinusoids as the convolution kernels. We will come to that everything in detail to identify 18 individual and 12 appliance combinations. Classification accuracy is enhanced by using a new activation function named SL-ReLU, okay, which is an adjustable logarithmic function along the soft sign and ReLU function. Other than using ReLU function, it is the modified function is used, and why, we will come to that. So, this is the data collection setup. You can see that current data is collected with the help of this architecture. This is the overall lab setup. Total 18 different single appliances are current data is considered, that is air conditioner, blender, CFL, CD and henceforth. And combination of that is also, because it is very common that in your home multiple appliances are turned on together. So, you have to identify which appliances are on. So, for that multiple combinations of the appliances are also considered. So, 18 different single appliance and 12 appliance combinations, the data from there are recorded for a 20-second time interval for 500 samples per second. That means total 10,000 samples are collected. So, this is a typical current waveform for few single appliances. This is for the desktop, this is for the AC, this is for the incandescent light bulb, this is for the washing machine and this is for the CFL. So, you can see their current signatures are different from each other. So, if your learning module can learn these signatures, then you can identify, okay, now my desktop is on or now my washing machine is on. Okay. So, now my AC is on. So, you can see that whether if AC is on, that means a thermostatically controllable loads is on for the demand side management. If my washing machine is on, that means a deferrable or a flexible load or an interruptible load is on for my demand side management. If we see a bulb or a CFL is on, that means a critical load. If you turn it off, then you will leave in dark. So, a critical load is turned on and we cannot do with the DSM. So, this is the application from this current signatures. This is the multiple appliance current data set. You can see the on and off, with every on and off your current signature values are changing, okay, from the AC and all of them. Okay. So, now what is convolutional neural network? It is mainly used previously with as in 2D for image processing, while you will give in an input feature, that is your input feature map. You have a filter over here, that filter will do the convolution operation and give you a convolved output feature. Then you can use the pooling layer, that is for maximum pooling or average pooling you can use. Then you flattening and you have a fully connected layer for the classification output. So, you have input layer, convolution layer, maximum pooling layer, fully connected layer by flattening and hidden ANN layers, and then you have classification with a softmax function. So, the main driving thing for this convolution neural network is that convolution filter that is helping you to get the convolved output feature out of it. So, if we can modify this filter, generally this filter, this is one kind of, you can say, physics informed neural network, okay, like physics informed convolutional neural network. Other than that, if you go for random one, it will randomly select the kernel, right. It will randomly select the kernel and then it will give you a classification with a very deep neural network you need. But if you can define this filter according to your input feature map, then obviously your size of the neural network will reduce. You do not need a very huge hidden layers. Also, your accuracy will be enhanced. So, that is done by using a multi-scale sinusoidal kernels by with this equation, where this parameter Fi and Ri are Mn are varied between 1 to 15. So, you have two parameters, you have changes from 1 to 15. So, you will get total 225 kernels. Okay. Among them, if you put m equals to 10 and n equals to 15, then you will get the perfect sinusoids. You can see these are the perfect sinusoids with different amplitude. Other than that, it is a little bit deformed sinusoids. Now, why sinusoids? Because your sinusoidal kernels are implemented due to its high resemblance with the input features sinusoidal current. We know all our electrical equipment shows a sinusoidal current. Okay. Ideally, their fundamental component of the current is a sinusoid. So, if that is superimposed with the filter of a sinusoidal kernel, like a sinusoidal kernel slides over this data for collecting the features, then the superimposition will be good. So, only the data will be collected only from the sinusoidal area, not from this redundant area, only from this data area. Okay. So, that features whatever you will get, those are more dominating and very good features you can extract. So, this you can say as a physics informed convolutional neural network for appliance classification. Other than that, if you go beyond 15, that means if you take more than 225, so you can see the filters will become a straight line. So, that has no resemblance with the sinusoidal input current. So, then it is noted if your m and n is more than, then very less similarity with the sinusoidal waveform. Okay. So, this straight line kernels have very low resemblance. So, the sinusoidal kernel waveform is not able to extract rich features. So, it is just will overburden your system. So, restrict your number of kernels in the network to be 225. Among them, your this 15 are primary sinusoids and others are your secondary sinusoids or multi-scale sinusoids. This is the architecture of the CNN. We are using two convolution layers. In the first convolution layers, we are using that primary sinusoid, and in the second convolution layers, we are using all the sinusoids, like the total 225 kernels. The input current signal is of 10,000 samples convolved in a sinusoidal filter having a size of 15 cross 100 at the C1. So, every filter is of a 100 size and total 15 numbers of filters are used. It is noted that during the instance load switching of the appliance combination, the recorded current signal undergoes a transition, and hence to extract a deeper features, multi-scale sinusoidal kernels are introduced by varying n and m into 1 to 15, and these are used at the C2 layer. Okay. Now, we will see that we are every convolved output features we use a activation function to nullify or to omit out the redundant data. Usually convolution layers are associated with an appropriate activation function. Generally ReLU or SeLU is used. What ReLU does? ReLU does that you will nullify all the data which are below 0 value and only take the positive values. SeLU says, okay, take the positive values, that is fine like a ReLU, but you can slightly activate a slight amount of negative. Other than just removing them out or throwing them out, you can use a little bit of negative data as well. However, if you see the current combinations or the current features we take, here some certain transients, and these transients generally occur because of the switching. When you switch, it will do a spark. So, that spark means a very high current will flow. So, that spark will give you a very high current like this switching on and off, but whether this is carrying any information, that high current, yeah, obviously it will say that at that time you have switched on something, what on that it will not say. Okay. So, this kind of a feature, if you take this feature out, then it will dominate your other features, because this current is comparatively very high compared to this level of current. So, if you take a feature out of it, then your convolutional neural network will be biased to that instant, and it cannot recognize which device is turned off or turned on. So, for doing that, we have introduced a new activation function that is called SL-ReLU, which has the benefit of the ReLU, of the SeLU, and as well as a new log function which will mask if your input feature value is very high. That means, for as ReLU for a positive certain amount of positive values, it will consider the exact value. For as a SeLU, it will use soft sign function to activate little bit of negative values as well. But whenever you will incur a very high value in the features, it will mask that with the help of a log function. So, bounded output for large positive input, and that will give you a very good feature. Other than completely nullifying it, you are just masking them or capping them in a limited or in a upper or lower boundary. So, this is the equation of your SL-ReLU function. This is your soft sign function, this is your soft sign, this is your ReLU, and this is your log. So, three parts depending upon the value of the input feature. Okay. So, the validation is done with the total 2479 data sets of single appliance and 28939 data set of multiple appliances, and then 50% of the data has been selected for training and the less 50% for the testing. The training process will terminate if the maximum number of epochs, that is 100, is reached. Varying learning rate is used because at the starting you need to go for fast convergence. So, at that time the learning rate is high for the last 40 epochs. Then at the medium you have to little bit slow down yourself, otherwise you will mix the optimal point. Okay. So, at that time the learning rate is reduced from the previous value, right, for the next 40 epochs. And at the very last you have to be very slow and you have to be very precise that you will hit the actual decision. So, at that time the for the last 20 epochs the learning rate is very low, okay. And then momentum value is fixed to 0.9, that you will get a good momentum, and mini batch size is 120, and we have seen the accuracy, specificity and the sensitivity values. These are the confusion metrics for the same. Only this is for the single appliances and this is for the multiple appliances, and you can see at most of the time the classification accuracy is very high and it is close to 0.95 and more than 95%, and most of the cases it is 100%. This is little bit less when we go for multiple appliances, because it is very difficult to get the actual multiple appliances. Sometime if you have two appliances, one current of one appliance dominates the other. So, at that time it will be misclassified as a single appliance, that is a very high chance of it. So, that is why you can say that sometime we got even lesser, the less than 90% accuracy. But however, for most of the cases the accuracy is good. Now, compare that with the traditional blindfolded convolutional neural network, where we do not have any kind of kernel initialization, that means it is not physics informed. Then what will happen? We have used plain learning, that means it is a complete, you just convolution pooling, convolution pooling like kind of thing. You have residual learning which has a skip connection, then you have a deep learning which is a concatenation layer. Okay. If you compare this, then you can see the accuracy. For plain learning, for residual learning and for deep learning, with that your accuracy obviously enhanced, that is the case. Plain learning possesses you the lowest number of accuracy. Then residual learning, actually some of the input features you are giving as a skip connection to the output, so that will little bit enhance your accuracy. Then in the deep learning you always take the output and the input and concatenate it and then supply for the next layer. What we have seen, you can see always you will take the input, then output, concatenate it, then feed it here, then again take it, then again take it, like all the layers will take the previous layers input and output. So, the learning process is good. So, little bit of higher accuracy you will see, but that will enhance your training time very significantly and as well as your testing time. Okay. So, if that is the case, then you cannot rely on it. This testing time is for the entire 50% data set, not for a single instance. For single instance, that is less than even 1 second. Okay. Now, for this MSK CNN, or when it is a physics informed CNN, you can see with only 2 layers whether you have here multiple layers, multiple DL blocks, and each DL blocks has 3 convolution layers. So, 3, 3, 3, so you have total 9 convolution layers. Okay. In between that you have max pooling, here also you have 1 convolution layer. So, total 10 convolution operations you are doing. So, other than that, in the MSK CNN you are just have 2 convolution layers with the proper kernel initialization. With that only you are getting higher accuracy of 98.61%, and the training time has been almost 1/3 of your actual deep learning if you compare this with the deep learning module, that is the highest level of your blind convolution layer. Okay? And your solution time is also less. Now, if you initialize it wrong, that means if your guiding principle is wrong and you initialize the kernels with a wavelet kernels, then also your classification accuracy will reduce. Okay. That even will reduce for if you use only the primary sinusoids. If you primary sinusoid, then it is 96%, with wavelet that will come to 94.81%. Okay. With our, that is 98.61. Now, you can see the convergence, we can see that obviously with the rolling epochs this will converge. Okay. Now, we will see how the SL ReLU will operate. So, you can see with the ReLU and SeLU, obviously the classification accuracy is good, it is more than 95%, but SL ReLU performs better and it give you the accuracy of enhancement of 1.36%, because you have masked out few of the unintentional or redundant features of those switching instances. Last application, that is the home energy management using ANN and RL. An hour ahead demand response algorithm for home energy management systems. To deal with the uncertainty in future price, a steady price prediction model based on artificial neural network is presented. That means, here you use a ANN module to predict the prices. Okay. In cooperation with forecasted future price, multi-agent reinforcement learning is adopted to make optimal decision for different home appliances and in decentralized manner. That means, you first predict the prices with the help of day of the week, hour stage, is a holiday or historical power demand and historical electricity price. Feed them to a neural network and you will get a forecasted energy price. Then you get that data to your reinforcement learning algorithm, and that will give you that whether running equipment will give you a minimum cost or not. So, that is done. If it is a non-shiftable, then you have no other option just to keep it on, no control over it. But if it is a shiftable appliance, then you can on it or off it. Even in the on, you can schedule how much power it can take. Let us say it is an AC and your temperature is always close to 22 degrees centigrade. So, you can switch off your AC. If it is a 23, the power consumption is little bit more, but not at the rated value. So, you have a good spectrum of the power consumption pattern. So, that you can get from your controllable appliances. Then you set the Bellman equation with the Q value, like you will note down the state and the action and see which actions will give you a reward, same like your reinforcement learning process with the Markov decision process. You will do an action, check the state and see whether the state is giving you a reward or not. That means, if turning on an equipment, if you see from this flow chart, the turning of on an equipment with a certain power level is giving you minimum cost or not, and satisfying obviously the constraints or not. If it is so, then do it. If it is not, then add the penalty. Then see whether it is the last hour. If it is the last hour, then not, then repeat the process and see whether you have converged to the optimal Q value or not. When each agent reaches the optimal Q value, that means you are doing decentralized. Each of the load will see whether turning it on or turning it off will add some extra value to the system or not. If it is so, then each one will have their own Q values set up, like own reward, cumulative reward setup. So it will see that obtained from the maximum reward, meaning that the sum of the reward is also maximum. So that will be your optimal path or optimal strategy. So this is the results. You can see that price prediction is quite good with the ANN, and that is the error level is very low. And with time, if you control the ACs, you can see by looking at the hourly price, the controlling has been changed. That means, when the price is low, more devices are turned on. When the price is high, the device turned on has been reduced. Again, at the off peak price time, your devices are turned on. That means, it is obeying that your energy cost must be minimum. And with that, Q value is also saturating. This is the convergence. If you solve the same problem with an conventional MILP problem, you can see the cost is around $129. But with the RL method, as everyone is deciding with a decentralized manner, so the RL method is giving lowest cost, and it is also converging after 500 iterations. So the number of iterations is high, but at least there is a fast acting thing, and it is a decentralized one. So with this, I will end today's lecture, and we end this AI topic, and we will continue with our next topic in the next lecture. Thank you.